India has taken a significant technological leap by initiating the development of its own Ring Laser Gyroscope technology for future submarine programs. This single step represents much more than a scientific advancement. It marks a decisive move toward complete strategic independence in one of the most sensitive sectors of naval warfare, underwater navigation. Until now, this domain has been dominated by a handful of technologically advanced nations, but India is now preparing to stand shoulder to shoulder with them. When a submarine dives hundreds of meters below the ocean's surface, it enters a world where external navigation references simply do not exist. GPS signals cannot penetrate seawater. And radio communication is restricted because even the slightest transmission can expose the submarine to enemy sensors. In this hostile, signal-denied environment, submarines rely entirely on an inertial navigation system (INS), a self-contained system that allows them to know their exact position, direction, and movement without needing the outside world. At the heart of the most advanced INS technology lies the Ring Laser Gyroscope. Unlike traditional mechanical gyroscopes, which rely on spinning rotors and bearings, an RLG uses laser beams to measure rotation. This shift from mechanical motion to the precision of light makes RLGs dramatically more accurate, shock-resistant, and maintenance-free. The absence of moving parts ensures reliability under extreme pressure changes, temperature fluctuations, and underwater vibrations, conditions that submarines routinely face. A typical ring laser gyroscope is housed inside a monolithic glass ceramic block made from ultra-stable materials such as Zerido. Engineers create a perfectly sealed triangular or square optical cavity inside this block. Within this cavity, two laser beams travel in opposite directions, one clockwise and the other anti-clockwise. The cavity is constructed using high reflectivity mirrors that ensure the beams keep circulating with almost zero energy loss. The key measurement principle is based on the Sagnac effect, discovered in 1913 but fully weaponized only decades later. When the gyroscope experiences rotation, the two opposing beams undergo a slight frequency shift. This shift, known as the beat frequency, is precisely proportional to the rate of rotation. Highly sensitive detectors measure this frequency change and convert it into incredibly accurate angular data. This is where the true power of RLGs becomes clear. They can detect angular changes as small as 0.001 degrees per hour. This level of precision is crucial for submarines that must remain submerged and undetected for extended periods. Over a long patrol, even a tiny navigational error can result in large positional drift. But with RLG-based INS, the drift can be reduced to as low as 0.5 to 1 nautical mile per month, making them among the most accurate systems in the world. To build a complete inertial navigation system, 3 RLG units are mounted at right angles to one another, each measuring rotation along one axis. These gyroscopes are paired with ultra-sensitive accelerometers that measure linear motion. Together, they form what is called a strap-down INS, meaning the system is fixed directly to the submarine's body and calculates movement as the vessel accelerates and turns. Modern algorithms further refine the data, allowing the submarine to maintain precise dead reckoning navigation without surfacing for weeks. India currently uses fiber optic gyros, FOGs, on platforms like the Scorpene-class submarines. Although FOGs are reliable, RLGs offer several major advantages. They are immune to vibration-induced errors, require no warm-up time, have higher stability, and provide far better drift performance. They also withstand shock waves from underwater explosions, which is critical in combat zones where torpedoes or depth charges may detonate nearby. These capabilities are especially vital for nuclear ballistic missile submarines, SSBNs like the Arihant class, that conduct stealth patrols lasting 70 to 90 days. During these missions, any transmission of signals, even a single GPS ping, can compromise the submarine's position and threaten national security. With a high-grade RLG-INS, an SSBN can navigate silently and confidently, staying hidden throughout its entire deterrent patrol. For decades, India depended on imported navigation systems for its submarines. This created a critical vulnerability. Any foreign supplier could theoretically degrade the system, deny updates, or embed hidden fail-safes. By mastering RLG technology domestically, India eliminates these risks completely. It also gains the ability to zeroize its systems, erasing sensitive navigation data instantly in case of emergency or enemy capture. Only a few nations, the United States, Russia, France, China, and the United Kingdom, possess the expertise to design and manufacture strategic-grade RLG-based INS systems. By entering this elite club, India not only strengthens its submarine fleet but also demonstrates a growing capability to develop world-class military technologies independently. This will directly support programs like the Arihant-class SSBN, Project 75 Alpha attack submarines, and future S-5 class SSBNs. India's decision to develop Ring Laser Gyroscope technology signals the beginning of a new era in naval warfare and underwater navigation.